We're back at the Poisson worksheet, version 1.1, question 2. So here we're actually going to apply the Poisson distribution to a word problem. So the problem is, suppose that in normal traffic conditions, vehicles enter the I-50 on-ramp at a rate of 10 vehicles per minute, with arrival times following a Poisson distribution. Alright, so what this means, just to give you a picture, is that you have an on-ramp, ramp, and the cars are coming on like this. Okay, there's your car. Zoom on the on-ramp onto the freeway. Alright, cut this out. So the way to approach this, you first have to define a random variable. So we say let x be the number of cars entering on-ramp. In 1 minute. Okay. Then we suppose that it's Poisson with rate lambda equals 10, so 10 vehicles per minute. So x is distributed as Poisson 10. Then what's the probability that exactly 10 vehicles enter the on-ramp in a given minute? That is the probability that x equals 10. So you could just apply the probability mass function, which is right up here. Okay, so we'll grab that. For our reference here, so we know what we're using here, we have lambda equals 10 and x, or k rather, equals 10. K equals 10. Applying that, we get e to the negative 10, 10 to the 10th power divided by 10 factorial. So now you go over to your calculator, plug this in. Here's an online calculator. Okay, so this is running our code online, but you can see that if we just use the definition here, this is the definition. E to the 10th to the negative 10th power times 10 to the 10th power divided by 10 factorial. Okay. When we can now run this code, and we see that we get some answer, 0.12511. So that's the answer if we were to just plug it into the calculator. Like, consider this the calculator. But because we're using a computer, we might as well just use the easy way to do this. And that's to just use the probability mass function here. So this is equal to 0.12511. And this built-in probability mass function, dpoise here in R, if we're just going to use R online using this RD, RIO thing, this is the probability that x equals 10 for if 10 is your lambda. All right, part B. I know some people had a little trouble with this. It says, what's the largest value k such the probability that k or fewer cars arrive is less than 0.01? So let's set this up. That says that the probability that x is less than or equal to k should be less than 0.01. And we want the goal here is to find the largest k, such as this statement holds. Okay, so then one way to do this is to start adding up things. Probability that x equals 0. Well, this left-hand side, this is equal to the probability that x equals 0 plus the probability that x equals 1 plus ... plus the probability that x equals k. So you have to add up all the probabilities that are less than k. We can again use the same calculation as above. They're exactly the same. Each one is the same. We just have to do enough of them until we start getting this. So one way to do this, again, using rdrr.io snippets, I can run this. That is, I add the probability mass function for 0, 1, 2, and 3 all together, and I get a number 0.0103365. So this is larger than what we're looking for. We want it less than 0.01 here. Okay, so that means that the number that we have there, 3, is too big. Okay, and I showed these two different function calls just to show you what it does. So this p-poise here, that's the cumulative distribution function for the Poisson random variable with a parameter lambda equals 10. So if we add up all the probability mass functions under 3, we get the same answers here down below. Okay, then, so if we take this line out, we'll have the probability that it's less than 2. And I'll just compute it here also again to verify that I'm adding up the densities as well. So if this is less than 0.01, then we're good. So before we had, yeah, so it is indeed 0.002. So this shows that 2 is the largest such k that we can work. So I'll write that in words, what we just computed here. All right. That took a while. We got the CDF for 2 and the CDF for 3. Looking over here, this is less than 0.01, more than 0.01. That implies k equals 2 is the largest k there. So that is our answer. Okay. So this didn't really have anything to do with it being Poisson. We just had to use the CDF over here. That's the thing that really mattered, using the CDF. For any other distribution, it would be the same. We would just be replacing the cumulative distribution function here that we're using with a different function and maybe different parameters. But you would do the same general idea for any discrete random variable. There's a better way to do it, but I'm not going to show you that. I'll leave it as an exercise. It's even faster than what I did, but just one thing at a time for the moment. Okay. All right.